to Mike and Fabian, who will run the next session. So Mike or Fabian, do you want to share your screen?
I have to have it enabled. I switched computers. So I'm not sure.
I have the capacity to do that.
Nathan,
Nathan, you want as a co-host?
Michael co-host. I think I cannot. Only Nathan can. Yeah.
Okay, I should be able to now.
Okay, great. And Mike and Fabian, I think you guys are moderating your own thing, so I'll just let you take control of everything. And note that you're starting about 5 minutes late, so feel free to run 5 minutes plus over.
Right. Thanks.
Yeah. So let me just remind people. So you have 20 minutes, and for those that were not here in the previous session, let me remind that we are encouraging new people that have not spoken yet to not be shy and ask questions and participate so that we can all see each other. So yeah, I'll pass it over to the 20 minutes of introduction by Mike and Fabian.
Thanks. So I'll give some background and talk about problems from machine learning that physicists have contributed to. And Fabian will continue focusing on how machine learning can help physics. So the field has really changed a lot, just as every active field of science, string theory. And just to illustrate that, I'll talk a bit about my introduction to this. So I went to Caltech, in fact, not to study string theory because this was 1983, but to work with John Hopfield, who, as some of you will know, proposed one of the early neural network models, which is still used in machine learning. And so I've followed the field and seen many of these changes over the years. So let me start, because again, it's more physicsy than many of the other things in machine learning, with this Hopfield model. And you can see a Hamiltonian energy, and basically it's a spin glass. So the S's are two valued spins here. Jij is a set of independently adjustable couplings. So there's no symmetry. It's a disordered system. And Hopfield's idea was to use this as a model of memory, to postulate a dynamics rather than a statistical interpretation, where if you start with a given configuration of spins, the system would be attracted to one of a few memories, special configurations. And so it's sort of associative memory. And it's easy to see that if you take a sum of terms, memory, tensor product memory, the second line here, then the configuration that is close to one of the given memories, the term that has the largest dot product with that memory will dominate and attract it to that. And then a good deal of work at the time showed that this is fairly general, but there's a limit on the number of memories, in fact, linear in the number of spins. So there were many directions in which physicists and other scientists got into these problems. There was back then the field called natural computing, this whole topic of computational schemes inspired by one or another natural system. And perhaps the most famous and probably the most important of these early developments was what's called the Perceptron originally, and now is, of course, the feed-forward network. And let me, again, this is not any kind of history. This is more from my own point of view, but just to give a sense. So this early period, people, physicists were some of the significant contributions to neural networks. And there were important empirical work, such as the first successes with convolutional neural networks date back to the late 80s, Jan LeCun's net for digit recognition. But this was still the period when symbolic AI and expert systems was the dominant mode of thought. But that would change in what people in that field often refer to as the AI winter of 1990s. And there was not much sense of what would work, but what was gradually realized over the 90s, I think, is that machine learning, although you can draw on physics and many other sciences, is most naturally a subfield of statistics. And again, that's kind of taken for granted now, but that was a recognition that various people had to make. And in our field, one of the very early people to get into this and write such papers was Vijay Balasubramanian. So you can look at that example as a how those sorts of connections were made. I'll come back to this topic of phase transitions and combinatorial optimization, which is a very direct influence of physics. And having this type of foundation on statistics, one could then be systematic and decide, how did machine learning, what were problems it was adapted to, and were very simple models at first, and really, it was the 2010s, of course, the famous AlexNet solving the ImageNet problem in 2012, and most famously of all, AlphaGo, GPT-2, to the point where it's clear great breakthroughs have been made, and they clearly have more scope that leading to this great excitement. But again, as in many fields of science, there's this almost universal phenomenon that after the initial ideas are formulated, they tend to go through this significant period of being unfashionable because it's just very hard for a variety of reasons to realize the potential. And in the case of machine learning, it was as much the need for much more powerful hardware than as anything else. Okay, so now let me, for the benefit of people that haven't seen this or just to set terms, here's a few of the standard machine learning tasks. So supervised learning is this, the basic example might be classify images into, label them as, this is a cat, this is a dog, and so forth. And then the computational and mathematical version of that is that what you're basically doing is fitting a function. The image is encoded in pixels. It's a big vector of intensities. And now you have a function which tells you, either what class, or more commonly, what is the probability the image is in a certain class. And you need to fit this function given a set of examples and hope that it generalizes. But again, any problem involving function fitting, this technology can do something for you. And of course, a great number of problems can be phrased in that way. There's probabilistic modeling, okay, which in the machine learning literature tends to be called unsupervised or self-supervised learning, where there's only X's, there's no Y's, there's some sort of input distribution, and you're just trying to learn the distribution. And this obviously has many, in fact, very clear scientific applications. One that a number of people have developed is to just say, well, what's the most straightforward and general analysis of collider data? Well, we have an event that distributes energy in various tracks and the like, and there's a probability distribution that in principle we can compute given the standard model of the detector simulator, and then we can compare that with the observed probability distribution. And of course, these are incredibly complicated distributions, so just modeling it is a almost necessary ingredient of making that comparison. Reinforcement learning, Fabian will get more into this. This is uses these other things and is distinguished by the fact that you don't get immediate reward, but you get some reward. So when you play a game, you find out at the end of the game, did you win or lose? And then here I've reviewed the feed-forward network in a formal language. And maybe the point here is that it is a very natural structure that the original engineering definitions might or might not make clear. You have a sequence of alternating linear maps, act by a matrix on a vector, which I labeled W, and then a sequence of nonlinear maps, which I've labeled theta, acting on each component of the vector. And this ReLU function is almost the simplest thing you could imagine, and it works just, in fact, in some ways better than more complicated functions like tanh. And then even two layers of this, W, theta, W, if you have a high enough dimension intermediate space, this is a universal function approximator, but it's advantageous to allow more layers and get simpler descriptions of the functions it's trying to learn. So the idea is that just adjusting the coefficients of these matrices W gives us this huge class of functions. And at this point, there's again, vast amount of hardware, software for doing that type of function fitting. And then just to complete the story, for supervised learning, we would define some loss function that tells us how close, or what's the error compared to how good the function is for our purpose. So it might be classification, and we would talk about how well the function models the correct classification that we're given. And then we just do gradient descent, say some numerical optimization within that class of functions of this loss function. And then of course, that's, again, it has this nice, simple conceptual starting point. And then one could, easily give a course or 2 courses on this. And the physicists are already contributing quite a bit at this level. So just as an example, work of Miranda Cheng and collaborators recently, the convolutional net is good for translationally invariant input distributions. But of course, you could have many other group operations and try to define distributions and networks adapted to those. Okay, so what does this have to do with physics? Okay, well, I'm going to go in both directions and tell you first, well, what are some of the questions that people do machine learning think are the essential questions? And so the most important that everybody would agree is, how do these models generalize? So if we have a function that tells us for an image what class is it, we've only given this negligible subset of the possible images. And the whole point is that it can classify images that it hasn't seen before. And in statistics, there was this kind of paradigm for answering this, which I'll say a bit more about, that you have a model that encodes prior information, say, about the spaces of images. But one of the great lessons of these recent successes is that you do better often by not putting in all these priors and using these very general models, such as the feed-forward network, which knows nothing, or the convolutional net, which only knows translational invariance. And then that is, in general, often more powerful than these models that know something. And so there clearly is some sort of more general mechanisms that are really not well understood. Now, there's a more specific paradox if you want something, a little better defined. The successful models have very large numbers of weights, these matrix elements W, and often so many that you can completely fit the training set. Now, if you've taken any course in statistics, you know that that's a bad thing to do, that if you can fit all your data, then you're overfitting, you're fitting all the noise, and you're not going to generalize. But that's not what happens here. And this has been sharpened, this paradox, to what in recent literature is called the double descent curve. So this is considered to be a central thing to explain. So if from your statistics class, you might recognize the left-hand graph here, which is the number of parameters basically on the x-axis and the error of the system on the y-axis. But the modern picture that comes out of machine learning is on the right-hand side, where there's a point exactly where you get enough parameters to fit all the data. And then as you add more and more parameters, you do even better. So this interpolation threshold. And so the curve goes down twice. And you often work in the second branch where it's going down the second time. And so how does that happen? So that's a much more crisp theoretical problem. So yeah, so I'll give 2 or 3 more, and then I'll give it to Fabian. So how do you do data, theory in a data-driven field? Well, you tend to have to make a synthetic data. And one way of doing that is to use analogy to a disordered systems. And that leads fairly directly to the idea of phase transitions in these theories. And the original Hopfield model had a phase transition where you put in enough memories. And then this is something you can study using the replica method and other physics methods. So this has been a point where physicists really contributed even the conceptual framework for understanding phase transitions. There's a natural method from a theoretical point of view called teacher-student, where you have one model that produces the data. Say you give it some X and it puts out the Y, and then you study the problem of how does the second model learn to fit the thing produced by the first method. And again, there's a lot of statistical physics which is directly applicable. Random matrix theory is one of our go-to tools, which has been much used here. And in fact, I'll recommend the work that derives the double descent curve in an interesting class of models using free probability of Adlering and Pennington. Okay, so let me say a little bit about what machine learning will do for physics, and Fabian will say much more. So, again, on the 30, 40-year time scale, all bets are off. Life may be revolutionized, but on the decade scale, it's clear that machine learning for science will do a lot of useful things. But what about conceptual influences? Okay, my own following this field over my career had many influences on me, and one was this interest in statistics of vacuum. It came out of, in part, studying statistics for machine learning. There's statistical concepts that you can use to study physical models, and especially spaces of quantum field theories. Again, Vijay Balasubramanian has written many works in that direction. you could try to make direct physical interpretations of architectures. There's an interesting paper of Akutagawa et al. That relates the feed-forward network to renormalization group in the ADS and gets an interesting model of hadronic structure. I've been looking at another application, which is a very machine learning thing. I'll leave this slide for your later reference, but there's, I think, a lot of reasons to think that mathematical research will be far easier to perform within a decade. The technologies that just as we use symbolic math quite often now, we'll be able to do many more things in terms of verifying and proving theorems. And finally, fundamental roles of physics in computation. And again, my interest in this was rekindled by Scott Aronson's 2005 thesis, basically about sharpening the point that physical systems can't do NP-hard computations efficiently. And of course, complexity theory in physics has become much more popular in recent years. And I think this field of applying it to get new insights into cosmology is a very interesting start that I've made in related papers of Curry, Alexander et al. Recently, that if you try to think of the vacuum selection not as say eternal inflation, but as non-equilibrium process and perhaps a computational process, you get many, many different insights that I think will be important. So with that, I'll let you go, Fabian. Let me, there.
Let's thank Michael while Fabian sets up the share screen. Yeah, we can.
I hope you can hear me and you can see my slides.
Yes, we can.
Okay, good. So let me go ahead with the second part. So the question I want to ask here is, are AI techniques, or I will focus on neural networks, are they appropriate tools for string theory? After all, as Mike just discussed, neural networks are just sort of a combination of affine transformation and nonlinear functions. They are universal approximators, so they can, in theory, learn any function, which can be a bad thing. I mean, you're sure they can learn the function you're interested in, but they can learn arbitrarily many other functions you're not interested in. So it's a question of what do they learn in practice, and then what tasks are they good at? But one thing that time and again they have proven to be good at, and it's not really understood why, is they're very good in pattern recognition. So they're used in self-driving cars, for example, or they're used to play Go and chess, which probably also requires some sort of pattern recognition under the hood. So in string theory, there are also patterns in the solutions. For example, here, these are the solutions of some flux vacua. And you might hope that it can pick up some of these patterns and help us find solutions. The second thing that they are very good at is natural language processing. And again, in physics or in string theory, these appear as discrete non-abelian groups where you have word problems that you're trying to solve, shortest word problems, for example. And they show up in, for example, grades when you study knot theory. And thirdly, there is this thing that Mike talked about, the double descent. So it defies common Lorentz statistics that they generalize well and they do not overfit, even though you have included many, many parameters. So you can just vastly overparameterize the system and you get a very good result. And there are many ways of applying sort of these three properties. I will be only talking about two because I don't have so much time. So one is to use it for conjecture generation. So using the fact that it generalizes very well, and to try to learn a map between quantities which are not known to have any relation. If the neural network performs very well, so that it finds a map that maps these far above the expectation, if it was doing something randomly, you might conjecture that these things are linked, and then you could hope to go and improve it. And this has been done in, for example, applications to knot theory, toric geometry, line bundle cohomology, and Brunnother theory, as Miriam briefly mentioned, and many more aspects of mathematics, especially by Yang Ruehle. And a second, maybe more classical approach or application is optimization and regression. So you're just trying to use this to find solutions for system of equations, and has been used for searches in string vacua. And we had a talk by Mariana, which didn't use a neural network or an AI, but a genetic algorithm in order to find solutions. And then, as Laura mentioned, it has been used in solving partial differential equations for Calabi-Yau and SO3 structure metrics. So let me just briefly give you three examples for what I just said. The first one is pattern recognition Diophantine equations. So Diophantine equations appear ubiquitously in string theory because you have topological data and flux quantization and so on. However, asking whether an arbitrary given Diophantine equation has a solution, let alone finding one, is actually an undecidable problem. So this is in some sense from computational complexity point of view as hard a problem as it gets. However, you might think that the Diophantine equations come out of string theory are not an arbitrary Diophantine equation, but they have some structure which are inherited from the stringent mathematical consistency conditions. So what was done in the study is there was a set up a game reinforcement learning, which had targeted solving a particular set of coupled Diophantine equations, which were related to flux vector of type 2 orientifolds, and sort of hoping that the neural network can find some pattern because it's good at pattern recognition. And what was found there is that indeed, it can rediscover a human-derived solution strategy for this coupled Diophantine system. But if you let it do whatever it wants, it also came up with new, more efficient strategies of solving the system. And as a second example for conjecture generation and natural language processing, I want to mention knot theory. So for conjecture generation, so what Hughes did is he used basic knot invariants and then tried to see whether you can predict quasi-positivity, slice genus, or the Osotsavo tau invariants using these. And what Vishnu Jejala and collaborators did was they fed the Jones polynomial and were trying to see whether you can map onto the hyperbolic knot volume. And this actually performed pretty well. In the second part, what we did is we used reinforcement learning in order to get a provably correct result from machine learning. So we set up again a game, which was to find the unknot. You give a braid that represents a knot, and you're asking, can you reduce the number of crossings to zero in this braid, essentially? And the neural network will then give you a sequence of randomized moves so that if you had the string physically in front of you, you could do these types of moves and you could physically unknot the string. So you can prove that a given knot is the unknot. And we found that it performed very well up to 100 crossings. As a third example, I want to talk about interpolation and Calabi-Yau metrics. So for the purpose here, we just think of the Calabi-Yau metric as a map from K-logs and complex structure moduli space and a point on the Calabi-Yau into a permission D by D matrix. And so we parameterize this map as a neural network and subject it to the condition that it's complex scalar and Ricci flat, which means it solves a Morse-Ampere type differential equation. And we have seen the talk by Gonzalo where they also use it for, they also propose to use a neural network to study some other sort of geometric background. Then you can use these expressions for the modular dependent metric, as Laura explained, for Yukawa couplings to compute a massive string excitation, check swampland conjectures for the SYZ conjecture, and so on. So Irene in her talk really summarized swampland conjectures, and one of the conjectures was that the mass goes exponentially with geodesic distance. So what we did is we used this neural network, computed the massive string spectrum as a function of the geodesic distance. So we computed periods, computed the geodesics in complex structure moduli space, and we found that the value with which the tau becomes exponentially light is indeed given by this 1 over square root 6, or it's very close to this 1 over square root 6 bound while satisfying it. And we also made this interesting observation that if you look at these different masses as a function of the complex structure, we found that there's a degeneracy in the system, which has to do with a symmetry that's there. And we found that irreducible representations under the symmetry group, if they're in small irreducible representations, they become lighter as you make the complex structure larger, as you move in complex structure space, and others become more heavy. And the ones that become more heavy are the ones that have a higher irrep, that transform in a higher irrep of the symmetry group, which is very interesting, and I would like to understand why that is. So let me summarize and outline future directions, also to form a basis for the discussion. So one big area of application is to search for string solutions or to use adversarial training in order to delineate the swampland landscape boundary, which is what Marianne and her group did. They sort of tried to incentivize their algorithm to go as closely to the tadpole as possible. So you could imagine finding, if they had found a counterexample, this would have sort of moved the boundary of the swampland further away, or would have expanded the landscape boundary. You can hope to get insights from machine learning where symbolic methods fail or just are not available, such as solving PDEs or equations of motions, for any background. As Sarah said, you can do this for reduced holonomy or for special structure manifolds. I briefly talked about computing massive strings spectrum, and it also has applications in knot theory. And then there are, of course, many other applications which I didn't even have time to cover. Random matrix theory, SYK or JT gravity. We had this nice talk by Jeff, where he had these graphs showing up in his SYK batteries. And when my monoreal graph neural networks can help study this, then there's mirror tensor networks, quantum information, numerical bootstrap, and integrability. So these are things that are, to the best of my knowledge, already being pursued. So to go into this discussion, let me end with open questions and speculations. So one question we can ask is, from a particular method you're applying, if it works or if it fails, can you infer something about the pattern that underlies the problem? So if they're good at pattern recognition, for example, and it fails, maybe this means there is no pattern to the solution, to underlying this the problem at hand. Then there are questions that have to do with computational complexity, asking whether approximate but fast results are acceptable. And this maybe hinges at the fact of whether or not, if the neural network gives you an answer, can you actually check that the answer is correct? And this has to do with which complexity class the problem is in. Or you might ask, can I even approximate the problem fast? If you cannot even approximate it fast, then there's no hope that neural networks can do it, because they're just bound by computational complexity as any other thing. And lastly, if you find an approximate solution, what do you require in order to believe that it is a solution? If you're doing this, for example, for cases where you don't have existence proofs. And then the last ones are maybe more vague or philosophical. So if consistent string theories are governed by Diophantine equations, which are undecidable, or any other problems which are highly complex in the computational sense, how did the universe actually manage to solve them? And asking this question, does it teach us anything about vacuum selection in string theory? And coming back to theorem proving that Mike very briefly mentioned, so let's assume that in the very distant future, an advanced AI was able to prove a theorem such that no human can go through or even understand the proof. Would we accept it, or would we even consider it a proof? That's all I wanted to say, and now I would like to open up for the discussion.
Thank you very much. Let's all
leave the slide on, or should I stop sharing?
You can. I suggest something. Please don't stop sharing yet. Okay, don't stop sharing. So let's thank Fabian and Mike for a very nice introduction. So now let me suggest, while we start the discussion, that people look at the questions and memorize them, but then we will stop sharing. I think it is helpful for a few seconds, but not for long. So please have a look and do raise your hand. And I would suggest maybe Jeff could say some words if he's around. He was not yet put on the spotlight in these discussions. Or I also see a contribution in the chat from Sergey Gukov. Okay, maybe they are not here.
Well, I'm here, but I don't have much to add. And yeah, thank you, Michael. Thank you, Fabian, for a very nice summary.
Okay, I encourage people to not to be shy. No one is going to blame you for not being an expert in machine learning.
Eva has her hand up.
Ah, yes, very good. Yeah.
All right, thanks, Mike. The problem is I spoke a lot last week, so they're trying to let new people contribute. Thanks a lot for the really interesting introductions and questions. I guess very quickly on this question of what do you do with an approximate solution? One thing that we played with recently is when it comes to these problems of the landscape and trying to solve the related PDEs, another thing that you can do is define a functional version of the slow roll parameters and treat that as your loss function. And then as you descend the loss function, you're actually happy getting, epsilon and eta, the loss, the slow roll parameters to be small, but not literally zero. It's of physical interest. So treating that as your objective function is already interesting. The other thing I wanted to say quickly is and Mike knows this, but not probably most people. One way that we can use physics to approach AI is, or to try and help with it, is in the optimization process. So stochastic gradient descent is like friction dominated motion. There are generalizations of that involve momentum. But in the world of descending cosmological landscapes, we have found other kinds of dynamics that are really qualitatively and quantitatively different. In that subject, they're called Pfx models. An example is dBi inflation. And so the slogan here is BI for AI, where what you do is you take the square root BI Born-Infeld action, and you make the speed limit such that it causes the motion in the spate of weights and biases to go to zero velocity when the speed limit is the loss function itself. So that is, it flies around according to the standard relativistic dynamics, but only stops when it should, as you reach the minimum of the loss function. And we are finding that works better in some well-definable circumstances, but we're trying to understand what people practically want from their optimizers, like what the specifications are that we should focus on. Is it minimizing the time spent optimizing the hyperparameters? Is it just solving some problem that no other can solve? And we found some examples like that. What should we, if one is trying to use physics to design the optimization procedure and improve it, what are people looking for? What are the criteria to aim for, aside from just going faster or solving some problem that the others like Adam don't?
Well, the deepest thing people are looking for is the quality of whether a model generalizes. Depends on there's like a lot of it's a very the loss function is non-convex. There are lots of minima. Some generalize better than others. People don't understand that very deeply. So, any kind of evidence, data insight is useful. But I mean, one fairly well commonly held idea is that if shallow or broader minima, so if below masses in physics language, a broader minimum will generalize better, and that actually just comes out of Bayesian statistics. And so that's a thing you can look for. And then people of machine learning have algorithms that try to do that, and they're not that efficient. So maybe there's physics-inspired way of finding a broad minimum.
That's great, thanks. I mean, what I was referring to was indeed very non-convex functions. So this approach flies over the barriers for sort of obvious intuitive physical reasons. Thanks a lot.
Maybe Sven, let me remind people, if you are participating, turning your camera on makes it for a nicer gallery view. So Sven, please.
Yeah, thanks. Thanks a lot for the talks, also in spirit of what Eva was saying. So one comment to add, I think, to this discussion is that there's a whole subfield of deep learning, which is geometric deep learning, which kind of unifies and gives an understanding of why certain architectures are working. And this, I think, beautifully plays into the role of how, which symmetries we are using. And so that's, a lot of interplay in terms of like building networks which obey these symmetries. And then there's a subsequent question, which also then comes into the play, is to actually find the underlying symmetries, because finding them for machine learning is very useful, because obviously if one knows about symmetries in the problem, one can then design architectures in the right way and get more efficient results for all sorts of problems. And that's very deep at the heart of what we also do in string theory a lot of the time, finding the underlying symmetries. And so that's another direction we are exploring in some sense with various works.
Maybe let me pass to Jeff and then Nathan, and then I will try to put some people on the spotlight from the chat again, so you are warned. Jeff.
Thanks, Pedro. Just to expand on the point that I was making in the chat, it was not so much that. So I don't really have any insight into applications to GR, but we're together with a student of mine and Daria Rosa, who's my collaborator on that quantum batteries, quantum many-body problem program. So we were trying to understand the ergodic MBL transition in these quantum many-body problems put on graphs. And as Fabian pointed out, graph neural networks are a great way to explore this space. And one of the things that we've been trying to do is, I guess what Mike was talking about with this student-teacher system, where you can have cross-learning, where you can train a network on a particular problem. Like, if you've got a kid trying to learn to walk and then you learn to run, those are two different sets of things, but learning to do the one gives you information and insight into how to do the other thing. So we're trying to use a neural network trained on a really simple, let's say, Heisenberg's spin chain with nearest neighbor interactions, and then tweak the Hamiltonian so you can have next to nearest neighbor interactions, or even go to higher order interactions, and see if the same network trained on the simple system can learn the many-body localization transition, the mobility edge, without retraining the network. So that's some of the things that we're thinking about in that context.
Nathan?
So I want to ask maybe Michael and Fabian to try to extrapolate. So Michael started already, but suppose in 5-10 years, I assume some areas of study are going to be wiped out by machine learning. Like we have a translator who I think will not have a job in 5 or 10 years. What areas of physics do you think will be most affected by this? And should students learn this and when they take physics classes? And
Yeah, I mean, I think physics deployment is pretty safe, for the next 10 years. I think the obvious answer is data analysis. There are all these kind of special purpose things that physicists and scientists developed over the years. And then in some cases, they're special cases of much more general techniques, or there's a general implementation that can do this much better. I mean, there are many examples in our field, or at least in particle physics. Work of Jesse Taylor is a good example, where a lot of the custom statistics for describing jets and collider events are actually special cases of things that if you talk about just statistics of energy distributions, the computer can learn itself. So data analysis. And then in other fields, and I would like to see more of it here, of course, there's this, huge excitement. And I mean, again, if you ask a machine learning specialist, our problems are very fringe, and what they want to do is help people discover drugs. They want to take these huge databases of drug activity or protein folding or this or that and discover new drugs. And, again, that clearly will revolutionize many areas of science, and to the extent that we can make our problems as well defined as the problems in quantum chemistry, say, we will share in that. I mean, that myself is how I like to see string phenomenology proceeding. We may or may not be able to compare with real world data, but we can certainly ask sharp questions that machine learning will help us answer in great generality.
Yeah, I agree with Mike here. So us as string theorists, we are probably safe, but I would still say that it doesn't hurt learning this. So there are techniques that are, or I mean, there are questions, for example, the massive string spectrum, where I don't see any way of answering this in the near future. We need a Calabi-Yau metric, and there has been great progress in Calabi-Yau two-folds, for example. So we have an analytic solution for this, but this sort of relies on hyperkähler structure that you have on K3 manifolds, and so they don't generalize to Calabi-Yau 3 manifolds. Or even if you're interested in just this much more broader class of compactification geometries where you don't have anything like the Calabi-Yau theorem, I think these are really places where you can sort of get inspired by applying machine learning tools, or any tools that help you go beyond the case where you have an analytic situation, and you can come up with conjectures, or you can just see what's happening, like, for example, reproducing this 1/√6 bound that Irene was introducing, or then observing this interesting, and at least for me, surprising correlation between the degeneracy of a symmetry of the Calabi-Yau space and the spectrum because one can be computed very, very easily, and one is inaccessible without neural networks. So I think it would be interesting to understand things like this better, so it can serve as input of things you want to then study theoretically better.
Thanks.
So I would suggest maybe again randomly from the chat, maybe Ning Bao and then Watty Taylor after. Again, I don't know. I want to try to encourage new people to enter the discussion, but I don't know if Ning Bao is interested. So 1 second. Let's move to Watty first, and
Sure.
okay.
So yeah, I just wanted to poke
Jeff
for a second at one. Sorry, should I go ahead, Pedro?
Yeah, please go. Please
Okay,
go.
I just wanted to poke for a second at one of the questions that Fabian put up on his last slide, and maybe see what Mike and Fabian and others have to say about that. So one of the questions, if I remember correctly, Fabian, was, so in many cases, solutions of string theory are described by systems of Diophantine equations. And you said, okay, if that's true, how does string theory solve those? And I'm not sure I feel like that's the right way to think about it. If it was a dynamical equation, right? If we were talking about a differential time development equation, and we were asking, how does string theory manage to solve, or how does physics manage to, how do fluids solve the Navier-Stokes equation? Then there's a real physics question there, because you have to figure out how the dynamics occurs in the way that accords with that. But I think of these Diophantine equations as simply discrete equations that must be satisfied by the proper solutions, but not something that the physics in some sense has to learn how to satisfy. It just is a characterization of the solutions rather than something that some dynamical mechanism has to solve. So I don't know if either of you have any comment on that. Maybe this dates back, Mike, to some of your work of a number of years back.
No, I do. I'll let Fabian speak first if he wants to reply, and then I do have.
Yeah, I can maybe just elaborate what I meant by it. So in principle, I agree with what you said. If it's a question of complexity, so if you might just ask, so how do you, if a problem is very complex, how do I find, how do I solve it? In the case of Diophantine equations is a bit different in my regard, because it's not, I mean, it's really undecidable. So provocatively, you might say if the system at hand was undecidable, also the universe couldn't have solved it. So the question would then be, are all equations that we get from string theory actually decidable with Diophantine equations? And then sort of having the different solutions then is a question of sort of dynamically finding or hopping between the different configurations, different fluxes and so on. But there's this fundamental difference between questions that are just hard to solve or questions that cannot be solved at all.
But just to follow through for 1 second before Mike speaks. So even if the equations are impossible to solve in principle for some general class, the fact that they're characterizations of the string theory that, or whatever world we live in, or of solutions to string theory, means that they're features of solutions rather than that the solutions in some sense need to solve the equations. That to me doesn't seem very different, but maybe Mike, you have something.
So you would say that anthropically, or for whatever reason, string theory is bound to give you Diophantine equations that have that are decidable.
I'll continue and say that I certainly agree. I think I mean it's really the physical dynamics in the context where whatever dynamics is generating solutions is relevant as a non-equilibrium, and that's the case where you really care what the dynamics is. And the type of Diophantine equations we're talking about are, I agree, they're generally not dynamical. And there's a lot you can say about again, much more well-known established physics problems about if you look at the dynamics, you find that the physics can't solve a NPR problem, and there's a lot of Scott Aronson wrote a very good paper about that, which I recommend to people back from 2005, and so I do think that yeah, I mean, any kind of string cosmology is very exploratory at this point, given what we know about the solutions, the landscape, the dynamics. I mean, it still can be inspiring and help suggest more interesting questions. And I think again, I would recommend the second paper that I wrote with Denaf, Green, Zukowski, as my thoughts about this, that there really are pretty good reasons to think, from at least the picture we have of string cosmology and internal inflation that we have now is valid, that that's really not what describes the actual quantum cosmology, and that there is something non-equilibrium about the real quantum cosmology. And the basic argument is just that the eternal inflation is so inefficient and seems to be dominated by configurations that are just so different than anything that we need to describe our universe. And again, I refer you to the paper for more well-defined, well-put versions of that argument. But I think this question of, so what are idealized but at least well-motivated non-equilibrium pictures of cosmology that we could build on is a very good one. And again, our paper, Curry, Alexander, et al., I think this is a area I would suggest people look at.
Let me see if someone is waving to discuss this type of topic. Okay, Jeff.
So just very quickly, there's kind of two sides to this story, right? There's the one side which is applying machine learning algorithms to physics problems, and then there's the other side, which is asking the question, why do these machine learning algorithms and statistical learning in general, deep learning, work so well? And it seems like, if we're asking about physicists having jobs after 10 years, if machines are doing everything. One of the things that it looks like there's a lot of development happening right now, which is trying to understand why these deep learning algorithms work, using, for example, renormalization groups, and something I pointed out in the chat that Eva raised actually is that Dan Roberts has a forthcoming book on deep learning that's very accessible to physicists. I think it's written in a language that we're all familiar with. It starts off with Gaussian integral and goes on from there. And there, the aim is really to try and understand why these algorithms work in a far deeper way than just, well, it's a computer science algorithm.
Maybe before turning back to Mike and Fabian, maybe we could go to the IIS node and then to Thorsten.
Yeah, so the way that the neural networks work and analyze images, for example, looks very reminiscent to the structure of tensor networks that we use in holography. And so one would wonder whether what's the relation and whether we can learn anything about one or the other subject by thinking about the similarities between these two things. I don't have anything concrete to say, but maybe someone has an idea.
Sven is waving, so I think he might have a comment related to this point.
Yeah, just as a comment. So there are studies actually trying to relate tensor networks and normal neural networks. So for instance, you could try to use tensor networks to do also like handwritten digit recognition. And so in that way, one can analyze the parallels. Yeah, that's just as a short comment on this. But in general, it seems to be the impression that neural networks have more functional capabilities than tensor networks.
Well, the biggest, there are many differences you could look at. But tensor networks are definitely a known thing in machine learning. And one of the biggest differences is that whether the calculations that you're doing have cycles or not, So feed-forward network, there's no cycle. You put in the input, there's a very clear rule for getting the output, and you don't need to solve, implicit equations, which you often do in other schemes, including most tensor networks. So that's why the feedforward networks are so much preferred in practice. But definitely there are problems where tensor networks seem to do better. And I think there is a lot to be learned and to make contact with physics ideas about them, yes.
Maybe Sven, if you have the reference, maybe if you could put it in the chat, maybe it could be nice for people. Thorsten?
Yes, thank you for the nice talk. So I wanted to come back to a point that Michael made earlier, namely that the applications of machine learning that are pursued in string theory are a bit on the fringe in the machine learning community, and that the areas where the major breakthroughs are happening in types of models and types of applications are not really a perfect fit for the problems that we would like to solve. And one of the areas that has seen major breakthroughs in these years is of course language processing, with the advent of attention-based models based on the transformer architecture, these GPT models, which have been trained on humongous amounts of internet data. And to me, it seems that maybe the biggest application to physics, and that could perhaps lead to the most progress, would perhaps be to use language models to leverage the information that we have accumulated in these thousands and thousands of archive papers over the year. So in some sense, like a search engine on steroids that could help you to more quickly figure out the papers, the information that is relevant to the questions that you consider. I wanted to ask what your take on that and propose that as another area that is worth exploring.
Yeah, I definitely think that will make a lot of progress, and that will be a very, very valuable tool 10 years from now. I will put up a link about a talk I have given, which spends a good deal of time on that type of question.
Sorry, Amir. Let's move to, oh, sorry, Ben. Let's move to Benjamin, actually, and then to Ben.
Thanks, Fabian, for the talk. I was just bringing attention to a slightly different tool, maybe related to some of the problems people have been talking about, where from geometric data or world sheet constructions you might have, for example, sets of constraints where you just don't know whether the equations may be unsatisfiable. So in computer science, there's these SAT solvers and SMT solvers, like satisfiability provers. And if you can get those constraints into a form that those solvers can understand, then they can be very fast at telling you if there is a solution or whether you've got a sort of theorem like a no-go theorem in their absence. So yeah, I just wanted to mention that if it's interesting.
Yeah, this comes back to the computational complexity problem. So if you have an idea of the computational complexity class your problem is in, for example, if it is in NP, you know that it can be mapped by definition onto a satisfiability problem, and then you can work out this map and use these SAT solvers to solve it, and hopefully quickly. That's one approach you can take. But of course, if your problem is harder than that, SAT solvers won't help.
Ben?
Yeah, it's related to what people were saying, but it's exciting to get AI to help us solve problems. But I mean, the task of just learning how to write an archive paper that string theorists will cite, it seems like there's plenty of data available for that problem. And I mean, I'm not at all an expert on this area, but I would think that in a decade you could devise a system that would succeed at that task. Better than we do. Is that off base?
Well, there are a few people out there, like Christian Szegedy is a researcher at Google, quite famous in machine learning, and he actually does believe something like that. I can put up a link, but most people do not. Most people, I mean, again, where are we at now? You can ask basic questions that involve kind of doing simple logic, word problems and things. And basically, computers cannot reliably answer those. It's just despite the language models don't have the ability to understand and do elementary logic in a reliable way. So it seems extremely optimistic to think that in 10 years. I mean, I actually in the end of the talk that I just put up a link to, and my talk has links to Christian and other people's works. I make a conjecture which, or at least I throw out an idea which kind of combines these things, which is to say that once the computers can pass that test, that they can kind of do elementary logical reasoning in a pretty reliable way, 10 years from then is when you might start to think they could start to perform human level mathematics. But yeah, I mean, I think by far the consensus is that we are at least 2 or 3 breakthroughs away from that kind of intelligence. And if people are forced to throw out time scales, it is this 30 to 40 time scale. And the more expert the person is in AI, the longer a time they tend to say.
I see. So you somehow can't just take the data from papers on the archive and
well, maybe you can, but there's some essential things the computers are not able to learn yet. So it shows up in this inability to really do basic logic on natural language. Obviously, if you formulate the problem as a logical problem in a program, it does it perfectly and very quickly. But melding those things together doesn't quite work yet.
Ning Bao is back, and I think it was very nice to hear his comments about complexity.
Yeah, so sorry I missed the earlier thing. Believe it or not, the theory experiment divide is not just something that exists in physics, but exists in computer science as well. So there's a lot of, I guess, mileage to be mined in the gap between the theoretical side of computer science, which talks about things like computational complexity, and the more experimental side of computer science, which is more like what machine learning and deep learning is like. And in particular, theoretical computer science, when they talk about computational complexity, are almost always talking about worst case complexity, because in general, it's very difficult to even define average case complexity. And so one should often be scared away if someone tells you that a problem is NP harder in some even more ludicrously large complexity class, because that's often a worst case result. And so that's a situation in which machine learning can be useful. And if one wants to be particularly ambitious, one could maybe even think about using machine learning to define a notion of average case complexity, because the way in which you generate your samples in machine learning could be the way, the distribution, if you like, with which respect you are attempting to define your notion of average case complexity. And I think that this is a notion that could be very useful in the physics context, because it would be very surprising to me if fundamentally uncomputable or extremely high complexity instances of problems appeared naturally in physics. And so ruling out those specific instances and knowing when those instances can be ruled out for certain types of problems may be a very interesting way of generating new constraints and paradigms that limit the kinds of physics questions that we answer by limiting the kinds of math instances that we use to generate our random samples.
Thank you very much. This is precisely what I had in mind when I wrote, and can the complexity tell us something about the vacuum selection process? So are there are only cases realized in string theory that are decidable or easy to compute? And you're completely right, and many problems that are NP complete or X-space complete even are solved approximately on a daily basis. For example, the turbulent salesman problem is solved by Uber and other companies every day. But yeah, so if the answer is indeed yes, all the equations that you get out of string theory are not worst case complexity, but are easier to solve, so that the universe could solve them or could solve them in 13.7 billion years, that's great. Or if the answer is no, it cannot be solved quickly, it cannot even be solved approximately quickly, so maybe the universe is still searching for the solution. I mean, of course, if it's related to consistency, this cannot be true. And that's, I think, the distinction that Bordy was aiming at. But yeah, you might ask sort of, is the problem solvable approximately, even approximately quickly, or is there no chance, is solving the approximate solution as hard as solving the fundamental problem itself?
But I also wanted to point out briefly that if the inverse of what I'm saying is true, it has profound consequences. So in the context of the work that you and Jim did on Diophantine equations, suppose that we found that some provably undecidable instance of which there are known many families of is embedded into string theory, and that somehow nature naturally solved or came to some near solution to this provably undecidable problem. If that's the case, then I think that that has actually potentially profound implications to what it means for string theory, that there is actually some undecidable mathematics, not even high complexity class, but provably undecidable mathematics at the core of it. And if that could be demonstrated or falsified, I think if it's falsified, it would go along with what everyone believes, but if it could be demonstrated, then I think it would dramatically change some of the questions that we ask at the foundations of strings.
Yeah, that idea is certainly out there. I mean, even defining the quantum gravity as a sum over four-dimensional triangulations is in some sense undecidable, because it's surprisingly, it's hard, it's undecidable whether a triangulation is a manifold. But yeah, definitely there's this kind of trying to work with physics on these foundational level, which again, many people have tried over the years. And I especially quantum mechanics, some other foundations for quantum mechanics. I mean, it's again, so many people have tried, but I think it's right. There's some deep thing to learn there.
Could you maybe just summarize for most? I suspect that some people like me don't know exactly what these undecidable things are and what we are talking about. It looks very esoteric, that there are equations that we cannot decide. Can someone give a brief summary for the layman of what are these mysterious equations?
So you
cannot just plug in mathematics and check if they are true or not.
So there are, so when you talk about complexity, there are different classes where you can say how hard is it actually to solve a problem. The simplest or the easiest class of problems is in P. So this means you can solve it in polynomial time, or you can verify a solution in polynomial time, but problems in this class P you can actually solve in polynomial time, like inverting a matrix, for example. Then there's the next class, this is NP, and this is short for non-deterministic polynomial. So these problems you can verify in polynomial time. So if somebody tells you this is a solution to the problem, you can actually check and say, yes, that's true. But you cannot necessarily find the solution very quickly. And it's a millennium problem, so if you want $1 million, you can show that or disprove that P equals NP. Then there are even harder problems. Lara mentioned, for example, Gribner basis computations. These are X-space complete. So this means you cannot, so this particular problem you cannot even solve, you cannot even check the solution in polynomial time. So if somebody tells you this is the answer, and you would have to compute it yourself to check it. And then sort of the highest level is a problem of decidable, like any decidable problem. You don't care how much time you spend on solving it. You can spend as long as you want, but you can eventually find an answer to this. And then it was sort of proven that there exist problems that cannot even be decided. So there are problems where you cannot devise any algorithm or any Turing machine, meaning any algorithm, that actually can tell you in a finite amount of time whether or not this problem has a solution. And the first problem was the halting problem. And this just asks, can you write a program that decides, given any input, whether this program will halt, will come to a stop, or will run forever? And you can prove that this is undecidable, this problem, by feeding this program to itself. And then you can run something like a Cantor's diagonal argument to show that this is actually fundamentally undecidable. And Hilbert asked actually in 1900 whether Diophantine equations were also of this type. And it took 60 years until Matjasevich, 60-something, actually proved that indeed Diophantine equations had this property that you could not decide whether they had a solution. And this is bound to the fact that you have an infinite, you don't have a bound on the length of the solution of a Diophantine equation.
Oh, okay.
If you have a quadratic Diophantine equation, there is a bound, and you can use this to solve a quadratic Diophantine equation, but cubic, or the most general one, is actually a quartic one. You can always reduce any set of Diophantine equations to a single quartic equation. And it has been proven that these are indeed undecidable.
Okay, but I can just plug the solution and check if it's solved. I don't know if it has a solution, but if I have a guess, I check, right?
Well, right. I mean, if there is a solution, then you specify all the variables. Of course, you can check that, but it could be that there's no solution. And now, how do you prove that?
Yeah, actually, if I could just interject, I thought the statement was that there were systems of Diophantine equations that did not admit a solution, but you could not prove within the axiom system of mathematics.
Yeah, that's right.
Peter just said, any finite system of Diophantine equations in integer coefficients make a countable list of all possible solutions.
I think you are breaking up, right? Is it not just for me?
Lottie, your last comment broke up.
Sorry, did I break up there? Or am I back?
You're back now.
Yeah, I'm sorry. All I was saying is, isn't the correct statement that there are Diophantine equation systems that do not admit a solution, but you cannot prove it within the axiom system? Whereas if there is a solution, you can always make a countable list of possible solutions and you will always reach it in finite time.
Yeah, yes.
Okay. So undecidable basically is only relevant when there's no solution. So I don't think that if string theory is solving it, it would fit into that category, because it would be a solution which could always be reached in finite time by simply counting all the possible solutions.
No, there's no bound. You cannot derive a bound for when you would find a solution, so you wouldn't know.
Absolutely, no. There's no bound on how long it will take, but for any
given and the gauge invariance
equation.
Equivalences also make this complicated. You know, as you know, like the problem of whether two four manifolds are homeomorphic is undecidable because the word problem for their fundamental groups is undecidable. So if your problem is not just to find a solution but to understand the gauge equivalences, you again have a problem.
Right. I'm just saying if the equations of string theory are a finite system of Diophantine equations and it has a solution, you can always find that in finite time, but it's unbounded how long.
I'm sorry, I would like to move to Ling Lin because he has not asking questions. And then let's close the formal part of the discussion and we can continue a little bit more informally. But let's move to.